5 cars that made engineers rewrite the rules. For more than 100 years, engineers have been chasing the same dream: to build faster cars, safer cars, smarter cars. For decades, the formula was simple: more horsepower, better tires, bigger wings. But in the 21st century, something has changed. Engineers stopped asking, how do we make cars faster? And started asking, what if we have been solving the wrong problem all along? One company built a car that creates race car levels of grip before it even starts moving. Another taught a 4-ton truck to move sideways. One supercar can even jump. Another combines the performance of a hypercar with enough room for 4 adults. And one Italian masterpiece actually changes its shape while you are driving. These aren't concept cars anymore. They are real. And every one of them forced engineers to rethink what a car could be. Hi, I'm Menge, a mechanical engineer from Ethiopia, and on this channel we don't just admire incredible machines. We rather uncover the engineering decisions that made them possible. Let's begin. The first one, the gravity Defier, McMurtry Spéirling. Imagine pressing the accelerator in a 1000 horsepower supercar. The tires scream, rubber fills the air. The car fights for grip before it can unleash all of its power. Now, imagine another car with even more brutal acceleration that doesn't spin its tires at all. It simply launches as if someone pressed fast forward on reality. Meet the McMurtry Spéirling, one of the most extraordinary engineering projects of the 21st century. At first glance, it looks almost too small to be taken seriously. But we could say appearances can be deceiving, because hidden beneath its bodywork is an idea that completely rewrites the rules of vehicle dynamics. Most high-performance cars rely on aerodynamics. Large wings push the car downward as air flows over them. The faster you drive, the more grip those wings produce. But there is one problem. At low speeds, they do almost nothing. The McMurtry solves that problem in a completely different way. Instead of waiting for the air to create downforce, it creates its own airflow. 2 powerful electric fans pull air from underneath the car, reducing the pressure beneath the chassis. The higher pressure above the car pushes it firmly onto the track, producing enormous downforce even before the wheels begin to turn. Think of it like placing a suction cup on a smooth sheet of glass. The harder you remove the air beneath it, the more tightly it sticks. The McMurtry applied that same principle, but to an entire race car. The result is astonishing. More than 4,000 pounds of downforce can be generated while the car is standing still. That means incredible grip the instant the driver accelerates. From 0 to 60 miles per hour in just 1.4 seconds. For comparison, that's even quicker than many Formula One launches under ideal conditions. And according to the company, the car can theoretically generate enough suction to drive upside down under the right conditions. Whether or not you will ever see that attempted outside a demonstration, the engineering principle is very, very real. To me, that's what makes the Spéirling so fascinating. It isn't just fast, it challenges one of the oldest assumptions in automotive engineering, that downforce must come from speed. In a future episode, we'll explore exactly how this fan system distributes forces through the tires without overwhelming the available grip, and why it's one of the boldest engineering ideas in modern motorsport. Here is the working giant, the GMC Hummer electric vehicle. If the McMurtry proves that small cars can rewrite the rules, our next machine proves that size doesn't even have to be a disadvantage in engineering. This weighs over 4 tons, yet somehow it moves like a crab. At first glance, it almost looks fake, but you are looking at one of the smartest steering systems ever fitted to a production vehicle. Most cars steer with only their front wheels. It's a design we have accepted for more than a century. Turn the steering wheel, the front tires change direction, and the rear wheels simply follow them. Simple, reliable, effective. But the engineers behind the GMC Hummer EV asked a different question. What if the rear wheels could steer too? The answer is a technology called four-wheel steering. At low speeds, the rear wheels turn in the same direction as the front wheels by up to 10 degrees. That small movement completely changes the way this massive truck behaves. Instead of carving a traditional turn, the entire vehicle glides diagonally. GMC calls it crab walk. Imagine trying to slide a refrigerator sideways through a narrow doorway. Normally, you'd have to twist, pivot, and struggle to make it fit. Now imagine the refrigerator could simply move sideways on a command. That's essentially what this truck is doing here. But making it work is far more complicated than adding another steering rack. Every fraction of a second, the vehicle's control system monitors steering angle, wheel speed, suspension position, traction, and driver input. Electronic actuators must keep all four wheels perfectly synchronized. If one wheel turns even slightly more than the others, the tires begin to scrub across the road surface, reducing stability and increasing wear. The software constantly adjusts each steering angle to keep the truck predictable and stable. It's a remarkable example of modern control engineering working quietly in the background. And this technology isn't just about making parking easier. Rear wheel steering is already finding its way into luxury sedans, high performance sports cars, and premium SUVs. It helps large vehicles feel smaller, more agile, and far more confidence inspiring. Sometimes engineering isn't about adding more power. Sometimes it's about changing the way a vehicle moves through the world. And here comes the dancing supercar. If our last vehicle challenged the way a truck moves, our next one challenges the very idea of suspension. At first glance, this almost looks like a special effect. A supercar dancing to a music, balancing on three wheels, even jumping completely off the road. But every movement you are seeing is real. This is the Yangwang U9, and it may have one of the most advanced suspension systems ever fitted to a production car. To understand Why it's so remarkable? Let's first think about what suspension normally does. Every car has a spring and dampers. Their job is simple: keep the tires in contact with the road, absorb bumps, and make the ride comfortable. It's a system that has served the automotive world remarkably well for more than a century. But there is one limitation within it. Traditional suspension can only react after the road has already disturbed the vehicle. The Yangwang takes a completely different approach. And instead of simply reacting to movement, it actively creates movement. Hidden beneath the body, each wheel is connected to a powerful hydraulic actuator. Unlike a conventional shock absorber, these actuators don't just resist motion, they generate it. Imagine replacing the springs in your office chair with 4 incredibly strong robotic arms. Instead of waiting for you to move, those arms predict exactly how much support you will need and adjust instantly. That's essentially what this car is doing. 4 times every second, a central computer constantly monitors wheel speed, vehicle acceleration, steering angle, and body movement. Then, in just milliseconds, it tells each hydraulic actuator exactly how high to lift or lower its corner of the vehicle. The result is extraordinary. The car remains remarkably flat through corners. It can compensate for sudden change in weight. If one tire is damaged, it can even continue driving on just 3 wheels. And yes, under right conditions, it can literally jump. Now, let's be clear. The jumping feature isn't designed to clear rivers or leap over traffic. It's a demonstration, a way of showing just how quickly and precisely the suspension can generate force. And that demonstration reveals something much more important. Modern suspension is no longer just a mechanical system. It's becoming a software-controlled machine. The future of ride quality won't depend only on springs and dampers. It will rather depend on computers making thousands of decisions every second. To me, that's a real breakthrough. The Yangwang U9 doesn't just absorb the road, it thinks about it. And that may completely change the way we design vehicles in the years ahead. Also, let me introduce you to the 4-seat hypercar. If someone asked you to describe a hypercar, you'd probably imagine something low, something loud, something with room for only 2 people. For decades, that has been the formula. Extreme performance demanded extreme compromise. If you wanted breathtaking speed, you left practicality behind. But Christian von Koenigsegg had a different idea. What if you didn't have to choose? This is the Koenigsegg Gemera. the world's first true 4-seat Mega GT. And it completely redefines what a hypercar can be. At first, the numbers almost sound impossible. 4 full-sized seats, enough luggage space for a weekend trip, and performance that rivals some of the fastest cars ever built. How is that even possible? The answer begins with packaging. In engineering, packaging doesn't mean the box something arrives in. It rather means finding a place for every component without compromising the overall design. Think of it like solving an incredibly complicated 3-dimensional puzzle. Every centimeter matters. The engine, the battery, the cooling system, the electric motors, the suspension, the passengers. Everything competes for the same limited space. Now, imagine trying to fit all of that inside the silhouette of a sleek supercar. That's exactly what the concept of Koenigsegg accomplished. The Gemera combines a powerful twin-turbocharged V8 engine with the company's revolutionary dark matter electric motor. Together, they produce an astonishing 2,300 horsepower, enough to launch for adults from 0 to 60 miles per hour in around 1.9 seconds. But speed isn't what impresses me the most in here. It's balance. Because despite all that performance, the cabin remains genuinely comfortable. Every passenger has space. Every seat feels intentional. Nothing appears to have been squeezed in as an afterthought. That's exceptionally difficult to achieve. It's easy to build a fast car. It's much harder to build a fast car that people actually want to travel in. The Gemera proves that engineering isn't always about choosing between two good ideas. Sometimes it's about refusing to accept the compromise in the first place. And that's exactly what makes this car so remarkable. And finally, here comes the shapeshifter. So far, we have talked about grip, we have explored steering, we have looked at intelligent suspension, and we have seen how engineers solved one of the biggest packaging challenges ever attempted. But our final invention is different, because this time the engineer isn't controlling the car anymore. They are controlling the air. This is the Pagani Huayra, one of the most beautiful cars ever created. But beneath its sculpted carbon fiber body lies an aerodynamic system unlike almost anything else on the road. Most performance cars generate downforce using a fixed rear wing. It's simple. As air flows over the wing, it pushes the car downward. More speed means more grip. But fixed wings always involve a compromise. A large wing creates excellent grip, but it also creates drag. And drag slows the car down. So, the engineers at Pagani asked a different question. What if the wing didn't have to stay in one position? And instead of using one large rear wing, the Huayra uses 4 independent aerodynamic flaps, 2 at the front, 2 at the rear. Each one moves independently hundreds of times every minute. Imagine holding your hand outside the window of a moving car. Tilt your hand slightly, and you immediately feel the wind pushing against it. Now tilt it another way, and the force changes completely. Now imagine a computer making those tiny adjustments every fraction of a second. That's exactly what the Huayra is doing here. Sensors constantly monitor the vehicle's speed, its steering angle, its braking force, and even how quickly the car is rotating through a corner. Then almost instantly, the computer decides which flap should move, how far, and for how long. Entering a left-hand corner, the inside and outside flaps respond differently to maximize stability. Braking from high speed, all 4 flaps rise together, creating an enormous air brake. Accelerating down a straight, the flaps lower again, reducing drag and helping the car reach incredible speeds. It's almost like watching the feathers on a bird constantly adjusting during flight. Tiny movements, huge consequences, and that's what fascinates me the most. The Huayra doesn't fight the air, it works with it. It's a reminder that some of the greatest engineering breakthroughs aren't about adding more power. Sometimes they come from understanding nature just a little bit better. As a summary, when you look at these 5 machines, it's easy to focus on the numbers. 1.4 seconds, 2,300 horsepower, 4-wheel steering, jumping suspension, and active aerodynamics. But those numbers aren't the real story. The real story is the people who refused to accept that something couldn't be done. Every one of these vehicles began with an engineer asking a simple question. What if there is another way? That's how innovation has always happened. Not by accepting the limits of yesterday, but by challenging them. And that's exactly why I started this channel. Because behind every incredible machine, there is an incredible engineering decision waiting to be understood. Now, I would love to hear from you. Which of these 5 inventions surprised you the most? Was it the fan-powered McMurtry, the sideways working hammer, the dancing Yangwang, the family-friendly Gemera, or the shape-shifting Pagani? Let me know in the comments.